This is EC 201 lecture 24. Okay. So far in this course we have seen what it takes for a device to give you incremental gain. From that we derived what the device characteristics must be, and we ended up with a two-port. Does somebody now remember what we called these terminals? 1 prime and 2 prime, and then we said that in the special case when the current in the first port is 0, okay, then for this two-port to have incremental gain, we must end up with characteristics of this nature. So if I plot I2 versus V1 prime, I must have Y22 is 0, okay, and by passivity the device characteristics must do this. Alright, and this curve stands for one particular value of, so V1 prime is some VA. Alright, so if I, no, this is for V1 prime. Oh, yeah, thank you. V1 prime is equal to VB. Now, then what did we say? We said the simplest case of a two-port network is when one terminal is common to both of them, or to both the ports. So we, in other words, said there is no 1 prime, 2 prime. We call this some terminal 3, in which case this still remains I2. Instead of having V2 prime, we have V2 3, and instead of plotting V1 prime, we plot 1 3 is equal to VA, V1 3 is equal to VB. Okay? This is all what comes out from simple network theory, right? And it indeed turns out that there is a device like this which exists, and that's called the PMOS transistor. And instead of drawing a boring black box, we draw something which looks a little more complicated for the symbol of the transistor. So then we get rid of the box, and this is what remains. Does it make sense? And what is the rationale behind choosing the direction of the arrow? The arrow on the NMOS transistor here is drawn in a direction so as to indicate coincide with the direction of current flow, and so the symbol kind of makes sense. And what did we say for VA and VB? VA and VB are, the MOSFET will not conduct for any old VA and VB. It will only conduct if VA and VB are greater than some minimum quantity called the threshold, and the threshold happens to be a positive quantity, in most devices. There is no earthly reason why VT can't be negative. If VT is positive, it's called an enhancement mode MOS transistor. One of you could have argued that, why on earth should these two be the common terminal? We could have chosen 1 and 2. That's a reasonable thing, right? There's no particular reason to be partial to 1 prime and 2 prime. So, if we said this is as legal a 3-terminal 2-port as the one we have seen before, we call this terminal 3 as usual. Since it's a pain to keep writing primes, I get rid of the primes here. So instead of having 1, the common terminal is basically the terminal on top. Does it make sense? In other words, when we went from here to here, what happened to the characteristics? Yeah, we replace the name of the terminal, but the nature of the characteristics didn't change at all. Now by the same token, what do you think will happen to the characteristics? When you move from here to here, what do you think will happen to the characteristics? They will stay the same except for a relabeling of the terminals. Must I call this guy here V32? Very good. What about, let me call this 2, okay? And this is, predicated on the condition that the current flowing through port 1 is 0. So this is the same as the original 4 terminal 2 port. And when we said that you can have a 2 port with only 3 terminals, then, one candidate characteristic is this one, which is the NMOS transistor. And if I, instead of choosing the lower terminals common, if I chose the upper terminals common, these characteristics also become a legal set of characteristics which are not precluded by theory of networks. Instead of having V11 dash is equal to VB, we have V31. If you wanted to come up with a symbol for this kind of chap, let me remind you that in the earlier case, this terminal was called the drain, the gate, and the source. Okay. So now by the same token, first of all, which do you think should be the gate? Okay, unanimously, this is the gate. All right. Which should be the other two? One of them must be the source. One of them must be the drain. 3 must be the. Which is the source here? The common terminal was called the source. Pardon? The common terminal was called the source. So by the same token, which should be the source here? 3, right? Match the following. And this, so the remaining terminal must be the drain. At this point, I'm not assuming any knowledge of devices on your part. Okay? We did something for the NMOS transistor. We use the same logic and come up with, what you would do with this animal. Alright? We need to find an appropriate name for the animal, but that can wait. And how does current flow? From source to drain. So now can you suggest a symbol? This is the gate. Okay. So any suggestions on the symbol? This seems to make sense. And we are used to putting an arrow in the source to indicate the direction of current flow. So what direction will you put now? Towards the arrow towards the left or towards the right? Left. So if the earlier symbol was logical for an NMOS transistor, this is logical for a device which has these characteristics, which are also legal and are derived from basic network theory. Now instead of V32, what do we plot? VSD. Instead of plotting I2, we plot the drain current ID. Instead of plotting V31, these curves are for different values of V31, which is now V source gate rather than V gate source. There are several differences, basically in the sign of various quantities. In fact, a device like this exists, and it turns out that's called the P-channel MOS transistor or the PMOS transistor. There is no earthly reason to have started off with the NMOS transistor. I could have done this before I did the NMOS. Okay. So this also can be deduced from the same basic principles that we have used to deduce the NMOS transistor. Does that make sense? By the same token as what we did for the NMOS transistors, what do we call this region of operation? We call this saturation. Okay. What do we call this region? This is the triode region. And it turns out that the equations for this device are pretty much similar to that you encountered in the NMOS case. You know, with the where we had used VGS, we had used VSG here and so on. Quickly enumerate the difference between the NMOS transistor and the PMOS transistor. It turns out, anyway, for those of you who have done devices, that the carriers of current in the NMOS transistor happen to be electrons. The carriers that actually conduct in the PMOS case happen to be positive charges, they happen to be holes. Let's see these characteristics. So, if the drain potential approaches the source potential, then the device is in which region? If the drain potential starts to approach the source potential, the device is in triode. Okay. So if you want the device to operate in saturation, which is when you get gain, you want the drain to be as far as possible from the source, but far in which direction? Above the source or below the source? Much below the source. In other words, you want the V source drain to be very large, which means that the drain potential must be as far below the source as possible. This is in contrast to an NMOS transistor where you wanted the drain potential to be as high above the source as possible. Does that make sense? In an NMOS transistor, you want the gate source voltage to be positive. In other words, the gate must be much larger than the source potential in order for the transistor to conduct. Okay? In the PMOS case, what do you see? The source must be much larger than the gate potential and enable the transistor to conduct. I mean, the arrow is the one that gives it away. If you want current to flow in the direction of the arrow, which side of the arrow must be at a higher potential? If you have a branch and you want current to flow in this direction, current always flows from higher potential to a lower potential, right? So this potential must be higher than this potential, which is basically indicating that the source must be at a higher potential than the gate in the PMOS case. The drain current flows into the drain of an NMOS transistor. The drain current flows out of the drain in a PMOS device. Does it make sense? So, in an NMOS transistor, which of these three terminals, the drain, gate and the source, which of these must be at the lowest potential? So, in an NMOS transistor, the source must be at the lowest potential. In a PMOS transistor, the source must be at the highest potential. Does that make sense? The lowest potential in any circuit is usually the reference potential of ground, and the highest potential is, VCC or VDD or whatever, right? So the source must be connected to the highest possible potential. Current in an NMOS transistor flows in this direction. The current in a PMOS transistor flows in this direction, but current is leaving the drain in a PMOS transistor but entering the drain in a NMOS device. This is VG, VD, VS, which happens to be ground. This is VS, this is VG, this is VD. In general, it's not necessary that the transistor source be grounded, so we'll keep it named VS. ID flows into the drain. ID flows out of the drain. For saturation, VD must be much greater than, we'll get into the specifics a little later, but VD must be much higher than Vs. So by the same token, for saturation, VD must be much lower than, in an NMOS transistor, VD can go 1 VT below VG. Now what happens here? In a PMOS transistor, by the same token, VD can go 1 VT. When I am pushing the transistor into the triode region, when VSD is becoming too small, correct? So if you look at this, you are pushing the transistor into triode when VSD is in this region where that means VSD is becoming close to 0. And you know that VSD is positive. So if VSD is becoming 0, it means that the drain is coming towards the source. VD can go 1 VT above VG. In an NMOS transistor, VGS must be greater than or equal to VT for conduction. What do I mean by conduction? For some ID to flow. Okay, regardless of whether the transistor is in triode or saturation, if some current has to flow through the drain, then VGS must be greater than some minimum value equal to VT. For a PMOS transistor, VSG must be greater than or equal to VT for conduction. Okay, in both cases, VT is positive for what is called an enhancement mode transistor. You understand? And it turns out that the equations for the PMOS transistor are the following: S, G and D Now can you tell me what the equation must be in saturation? It's the same form as the NMOS transistor. So ID must be equal to, as I said, mu n is basically the mobility of electrons in the NMOS transistor. So by the same token, here I told you the carriers are holes. So so you must use mu p is mu p Cox W by L times VSG minus VT times VSD minus VSD whole square by okay. So this is provided for VSD less than VSG minus VT. If VSG is very small, what did we see? We could neglect this term. Okay, and this between the drain and the source behaves like a linear resistor whose resistance is controlled by the gate potential. Now if VSD is very large, then it is 1/2 mu p Cox times W by L times VSG minus VT the whole square. Hey, so what is the great thing about this? Why is this like suddenly a cool thing to have? Please note one thing in both transistors. So whether you have an NMOS transistor or a PMOS transistor, current flows like this in an NMOS transistor, current flows like this in a PMOS device. It's always flowing from a higher potential to a lower potential. So if you operate the NMOS transistor in the saturation region, it behaves like a current source. Pulling in which direction? If you have access only to the drain, the transistor is sucking current into the drain, correct? Whereas when you have a PMOS transistor, you have a current source which is pushing current out of the drain. Having NMOS and PMOS transistors will give you the ability to have current sources which either suck current out of a node, or if you wanted to push current into a node, would you use a PMOS transistor based current source or an NMOS transistor as a current source? You will use okay, so you had some node here. You want to pump current into this node. The natural candidate is to use a PMOS device biased with a sufficiently large Vs and Vg, okay, so that this behaves like a current source. If you wanted to suck current out of this node, okay, what will you do? You have a NMOS transistor connected like this. The NMOS transistor, please note that the characteristics of the NMOS transistor are like this, where this axis is VDS. So if the drain is larger than the source, then the transistor will look like a current source, pulling current out of this node. And the PMOS characteristics look physically, similar, but this is VSD rather than VDS. Okay, so it will be able to push current into this node as long as the source drain voltage is sufficiently large. And in modern technologies, it's possible to have both NMOS transistors and PMOS transistors built on the same IC. And this technology where you have NMOS and PMOS transistors on the same chip, okay, such technologies are called CMOS, where C stands for complementary and MOS is metal oxide semiconductor. Okay, and NMOS and PMOS are basically, they're a complementary set because the PMOS can do stuff which the NMOS cannot and vice versa. And as you will see, going further in this course, it's very, very convenient to have the complementary device and opens up a whole bunch of nice new circuit possibilities, especially when you start putting NMOS transistors together with PMOS transistors. So these are the device characteristics. What are we interested in next? We're trying to build amplifiers with this kind of device. So the next thing is to go and try and find and when we want incremental gain, so everything incremental depends on the small signal properties of the nonlinear device. So what we try to figure out is what the small signal equivalent of this transistor looks like. It must look very similar to that we saw in the NMOS case. So let's just go through the motions and figure it out. What is the small signal equivalent of the transistor in saturation? If you like to think about it still as a box like this, I1 is still 0, I2 flows like this. It's just that these two have been connected together, alright, and this is what is there in the box. So what is Y11 of this 2 port? Y11 is 0, Y12 is 0 because the current in port 1 is 0. So it is there's no influence of port 2 on port 1. Y21, if I had this box, it would be nothing but dou I2 by dou V1, where V1 is the voltage across the first port. So what is I2? I2 is nothing but in saturation is 1/2 mu P C ox W by L times V SG minus VT the whole square. So dou ID by dou VSG is what we are interested in, which is mu P C ox W by L times VSG minus VT, VSG minus VT, which is also the same as 2ID by VSG minus VT, which is also the same as square root of 2 mu P C ox W by L times ID. I mean, the equation form is the same, so you're all used to how these expressions came about. The same expressions will have to hold because the form of the equations is the same. And what is Y22? Y22 is 0 because the drain current doesn't depend on the second port voltage. As you've seen with the NMOS case, what did you see is we said that which kind of cheated in the beginning. We said that the ID is independent of VDS in saturation. That's how we began. And then we said, oh well, it's kind of okay, but it's not quite true. There is a small dependence of ID on VDS. So you can expect the same kind of behavior even for a PMOS device. So in an NMOS transistor, if I increase the VDS, the drain current increases. Okay, even in saturation, where we expected the characteristics to be flat, the current still increases. In a PMOS transistor, when VSD is increased, in other words, when VD goes low, if I yank VD down, the current flowing out of the drain will increase. We added a 1 plus lambda VDS in the NMOS case. So what must we do in the PMOS case? 1 plus lambda VSD. Let's now figure out what the equivalent circuit is. The small signal equivalent circuit must be Y11 is 0, Y12 is 0 again. So this is the source, this is the gate, and this is the drain. So this is the small signal equivalent in saturation, where what is the strength of this current source? It's of the form Gm times VSG. We've always been used to the in the NMOS transistor case, what did we do? What were we used to? The voltage control current source has the arrow pointing drain to source. That's not a big deal because I can always make this VGS. The idea in doing this is that if you have a properly biased NMOS transistor or a properly biased PMOS transistor, it doesn't matter, the incremental equivalent for both of them is the same. I could very well put VSG and then leave it with the arrow pointing downwards, but this is a cleaner thing to do simply because the incremental equivalent circuit becomes the same whether you have an NMOS transistor or a PMOS transistor. So now let's see what this leads to. There are many ways of realizing the same incremental equivalent. We have seen this, the common source amplifier, we have realized using so many ways of biasing, but you push current into the drain, feedback here, feedback there, all sorts of stuff. Okay. So for a given incremental equivalent circuit, there are many ways of realizing it, even if you only restricted the implementation to contain only NMOS devices. Now, you see that for the same incremental equivalent circuit, you can also use PMOS devices. So you can see that now the number of circuits that you have has doubled because you have, everywhere you have an NMOS transistor, you can replace it with a PMOS transistor with the appropriate biasing. So the number of circuits will, and now if you think of combining NMOS and PMOS, the number of circuits will just explode. And the bottom line is that there's no point in mugging up topologies. What makes sense is to sit and understand how these things work, so that once you see a new circuit, you aren't all bewildered. So you can imagine when you put 10 transistors together, the number of possible circuits just goes to infinity for all practical purposes. All right. So when I add the channel length modulation, what happens? ID is 1/2 UP Cox W by L times VSG minus VT times Vs times 1 plus lambda VSD. And again, lambda is called the channel length modulation parameter, and in which case dou ID by dou VSD will be equal to lambda I. In which case the equivalent circuit of the transistor, instead of becoming like this, so this is the output conductance of the MOSFET, so the output resistance is 1 over lambda I. Does it make sense? As a matter of nomenclature, when you have a CMOS process, there is no earthly reason why the threshold of the NMOS transistors needs to be the same as the threshold of the PMOS transistors. So what do you suggest that we call the threshold of the NMOS transistor? In a CMOS process, VT N refers to the threshold of the NMOS devices. VTP refers to the threshold of the PMOS transistors. Lambda N corresponds to the, when there is no earthly reason why the channel length modulation parameter for the NMOS transistors needs to be the same as that for the PMOS. So lambda N channel length what are the units of lambda? Per volt. Okay. Modulation of NMOS transistors, and by the same token channel length modulation of the PMOS devices. See, people are typically used to thinking about the threshold as the minimum gate source voltage required. So often you will find that even though you expect for an enhancement mode PMOS transistor, you expect this VTP to be positive. Some people have this strange way of writing VTP as a negative quantity because they treat it as a gate source voltage. Okay, so to avoid that confusion, a lot of people sometimes write the equations as VSG minus mod VTP whole square. As the equations for the PMOS, especially when you open a devices book, can be pretty intimidating, which is why I always like to think about it physically, and you know that when you're confused, you always go back to the basics and realize that the PMOS is just coming from the same old 2-port parameters. It is just that instead of assuming that 1' and 2' were common, I assume 1 and 2 were common and the characteristics remain the same. So everything follows from there. There is no need to mug anything up. Everything is quite logical. Start making a common source amplifier. How do you make a common source amplifier with the PMOS transistor? Let's start with the very dumbest thing that you can do, which is what we did the last time around. For the NMOS transistors, what did we do? What is the very first step in trying to build a common source NMOS amplifier? We said for an NMOS transistor, we first need to bias it up in the saturation region. So, and that was accomplished by doing this. Okay, so we have apply a VGS which is greater than VT and a VDS which is greater than VGS minus VT. By the same token, can you help me figure out what I'll do for the PMOS? The direction of the arrow, okay, thankfully the transistor is different, yes. What else? What must I apply? I must apply a gate source voltage, apply the proper drain source voltage. So here what should I do? The battery must point which way? So I must do this, and what must I do here? Positive terminal goes up or down? Up. Okay. And if I want to bias the PMOS transistor in saturation, VA and VB are the strengths of the two batteries. Each battery must have a larger voltage if I'm interested in biasing the transistor deep in saturation. VB must be very large so that the drain can be made to go as far below the source as possible. Okay, now that you understand that, what did we say next? We said it's kind of a terrible thing to waste a battery. So you can derive one battery from the other. And please realize that in the PMOS case, the source must be at the highest potential. Correct? So this is RA, this is RB. Let's add the load. The drain. Okay. What is the potential at this node? VDD times RB by RA plus RB. So what will be how will I calculate the drain current in the transistor? If I denote VDD times RB by RA plus RB by VG, how will I compute the drain current in the transistor assuming it's in saturation? ID must be equal to half mu P C ox W by L times VDD minus VG, which happens to be the V source gate, minus VTP the whole square. That makes sense? So what is the quiescent potential at the drain? It's simply ID times RL. And for the device to be in saturation, ID times RL must be, will the device be in saturation if ID times RL is too large or too small? If ID times RL becomes too high, then the transistor V source drain will get too small, which means it will get into the triode region. So the condition for saturation must be ID times RL must be less than or equal to, remember in a PMOS transistor the drain can go one threshold above the gate. So ID times RL, which is the drain, can go at most to VG plus VTP. Okay. What is there to be done now? Okay, bias the device up properly, figure out the operating point. The next thing is to add the source and the load if another load where there is no DC current flowing through the load if necessary. So how do you add the source? Infinite capacitor, RS, Vs, infinite capacitor, RL1. I mean, how should I choose RA parallel RB in relation to RS? Just like in the NMOS case, if I choose RA parallel RB much greater than RS, then the incremental voltage here will be at the gate will be approximately Vs. So what is the incremental output voltage What is the incremental equivalent of the transistor? RL1, VG, this is RA parallel, RB, RS. The incremental gain V out by Vs. So if RA parallel RB is very large, this is approximately equal to Vs. So the incremental output voltage V out is nothing but minus Gm times RL parallel RL1 times Vs. Great. So we will wind up.